In this video, we will be covering some examples that relate to Gauss's law, checking out some examples of some different geometry relating to Gauss's law, finding an electric field for unique shapes, and finding electric flux. So these are our week 3 Wiley Plus questions, and our first question is asking us to find the different electric fields through different faces of a cube. We'll zoom in a little. So we are given an electric field with our direction vector, so it's not solely in one direction, it is at an angle. And we know that this cube has side lengths of 0.62 meters. So in this cube as shown, it wants us to find the electric flux through the top face, bottom face, left face, and back face. So how would we do that? Okay, so the first thing that we are going to do, we're going to write out our equation. So we know that electric flux is represented by this symbol phi here, and this is equal to our closed interval of electric field dot product dA. And in this case, our electric field is not constant. So no, not constant. Because like we said, it's directed at an angle, so it's not going to meet each point the same way because of that angle. So we are going to have to rely on keeping this dot product. And we're going to use this half of the equation. We don't need to use the Q enclosed because we are not given our charge. So we are going to stick with the left side of Gauss's law. Okay, so what do we know? We know that when we have our dA, that's like taking our face and directing a vector directly out from it. So we know that this dA for our top face, for A, is pointing upwards. So that means it's in the positive j hat direction. So that means we need to find the area of the top face and then just make sure it is in that direction. So let's write out for part A. So we're given our E, so it's 4.7 I, and we can get rid of the closed interval since we're only dealing with one face at a time, minus 7.2 y squared plus 1.6. This is our J, and we're taking the dot product of the area of our top face directed upwards, which is 0.62 meters squared in our positive j hat direction. So we don't have any k components, nor do we have any I components. So this I is just going to zero out because the I component of our area would just be 0. So then 4 times 7 times 0 would just be 0. Therefore, we are only dealing with multiplying these two together. So what do we plug in for y? Well, since we are at a distance of our side length from our origin, we are going to put 0.62 in for our y. So 0.72, 0.62 squared plus 1.6 j times 0.62 squared. And this is going to give us times, hold on, 0.62 squared plus 1.6 times negative 7.2 times 0.62 hold on, give me a second. And that will give us our flux at the top face is equal to negative 5.492, and our units are Newton meters squared per coulomb. Okay, so now let's apply the same principle for part B. Part B is asking for the bottom face, so we're going to want this section here, and directed outwards means that it's pointing in the negative j hat direction. And in this case, y is going to equal 0 because we don't have to travel that distance to, like we did for our top face, right? Because we're already on the xy plane. So let's do B now. So our flux is equal to our electric field, 4.7 I minus 7.2. Then our y is just 0 squared. It's 1.6 J. It's dot product of our area once again. J, and it's in our negative J direction. So again, that's going to zero out. So then we'll just have 7.2 times 1.6 times negative 0.62 squared in our J hat direction. And for our bottom face, that is going to give us 4.428 Newton meter squared per coulomb. That is part B. Awesome. Okay. Next up, we want our left face. So that is this section here. And we know that it's going to be directed outwards. And that is in our negative I direction. So for part C, (4.7 I minus 7.2 y squared plus 1.6 j times 0.62. So our area always remains the same, but now we're just in the I direction and we're negative. So in this case, we have two I components that can multiply together, but we have nothing for our j component. So that's why this gets crossed out. So we don't have to worry about plugging anything in. So that will be 4.7 times negative 0.62 squared in our I hat direction. And this will be 4.7 times 0.62 squared. It's going to be negative 1.806. Flux of our left one. Awesome. Then for D, we are asked to find through the back face. So if we did it through the back face, I'm just going to clear this up a little bit. If we went through the back face, you can see that in our answer it's already 0, so we can just explain this really quick even without needing any of that. So if we have our back face here, and it's pointing out in that direction, that it's in our negative z direction, or our negative k hat unit vector direction. We can see that in our E equation, there is no k component. So no k component in our electric field. So our flux will be 0. Finally, we want to find what it is through the net flux through the cube. So then we will just be adding up all of these values here. Let's see, we did our top face, bottom face, left face, back face. We know front face is also going to be 0 because, again, there's no k direction. So we just need to find our last one with our right face. Right face will just be our left face, but with a changed sign. So that is going to be positive 1.806 So if we add up all of our values, what do we start with first? So we have negative 5.42, 4.428. Both our front and back face are 0. Our left face, and we see that our right face is the same, and that these two cancel, so we're only going to add up our first two, so that's negative 5.492 plus 4.428, and this is negative 1.064 is our net flux through the cube. So it's important to note that when it's not consistent, you have to be using your knowledge of dot product and how each component is going to play a part in that equation. Okay, our next question, nice and simple. It wants the electric flux through the net. So we're given our electric field and our radius. So that means we can use the left side of Gauss's law, which is E dot dA. And since we're not given any directions, we know that E is constant. So we can kick it out of the integral. We're only dealing with one homogeneous surface, so that will just turn into E times area, which is E times the area of our circle because we want it at the rim of our net. So this is going to be pi r squared. Plug those numbers in. We have 5.4 times 10 to the negative 3 newtons per coulomb. And we have pi 0.089 squared. And what does that give us? That gives us 1.343 times 10 to the negative 4 Newton meter squared per coulomb. Nice and easy. Our next question is not so nice and easy, but that's okay. We're going to break it down step by step. So for this question, we are required to use Gauss's law and Gaussian surfaces to find electric fields at different points. So we have a conducting rod, which is our center, and this, so I'm going to write some notes with it as well. So we know our radius, our first radius is, let's convert this to so this is 0.0012 meters. It's our first radius. Our length of our cylinder is 11.8 meters. And we have a second radius, which is in terms of R1, so in green here. So I'm just going to do the math right here. So times 13, this is 0.0156 meters. We have Q1, that is on the shell. Sorry, net charge of the rod. Sorry, so that's for the inside part. This is equal to 3.73 times 10 to the negative 12. And lastly, we have Q2, on the outside, which is equal to negative 2.17 Q1, which is equal to 3.73 times 2.17, and that is negative 8.094 times 10 to the negative 12. It's going to ask us to find from different spots what the electric field is going to be. So I'm going to write these values down just on the side so I can clean this up a little bit. So this is 0.0012 meters. Our length is 11.8 meters. R2 is equal to 0.0156 meters. Q1 is equal to 3.73 times 10 to the negative 12 coulombs. Q2 is equal to negative 8.094 times 10 to the negative 12 coulombs. Okay, so I'm going to clean this up a little bit so we can move on with our question. So the first that it's asking us to do, the first point we are measuring from is at a distance of radius equals 2.16 R2, which we plug in our numbers is 2.16 times 0.0156, which is equal to 0.033696 meters. This radius is larger than both of our R1s and R2s, so this R is greater than R1 and, R2 and is greater than R1. That means if we were to draw where this is, we would draw it, so I'm trying to figure out what color to use. It would be enclosing our cylinder like this on that outside. So because of that, this Gaussian surface encloses both Q1 and Q2. So that means we're going to be adding for our Q enclosed. So the first thing we're going to do, we're going to find Q enclosed, our enclosed charge. So I'm going to keep them both in terms of Q1. So that means we're going to have Q1 plus our Q2, which was given to be negative 2.17 Q1. So that means 1 minus 2.17 is negative 1.7 Q. Negative 1.17 Q1, which is equal to 3.37 negative 12. So this is equal to negative 3.9429 times 10 to the negative 12 coulombs. So that's for A. That is our Q enclosed. So that is our right side of the equation done. And then our left side, we are given okay, so what do we know about our geometry for this? So we know that from our notes, scrolling back up, for a cylinder, a cylindrical Gaussian surface, we know that our top and bottom faces point perpendicularly with our electric field coming out of the line of charge, so therefore we don't include it, and we're only wanting to use the side of our cylinder, right? So we only want to worry about this part right here. So that's what we're going to use for this question down here. There we go. So of our side only. So then that is going to give, so we know that E is constant. So we're going to keep that out of the integral. And then this is equal to E times A. So we'll do all the work here because our process is going to be really similar for the rest of our questions. So that means we are going to be given E times 2 pi R L, where R is our Gaussian R. So let me elaborate on that. So our R is going to be from the new surface that we just drew, right? The one that I drew in fuchsia earlier. This is going to be the R that we use here in that equation. So when we equate them together, that gives us, so I'm actually going to label our steps. This is 1, 2, 3. So that gives E 2 pi R L equals negative, I'm just going to say Q enclosed. Plug that all in and isolate for E. So that is negative 3.94 times 10 to the negative 12 coulombs. E naught 2 pi, and our R we found to be 0.033696 squared. Then our length is given, our cylinder. So then plugging that all in, that's going to give 0.854 to the 12 times 2 pi times 0.036 times 11.8, and that is going to give electric field of okay. Hold on, I think I did something wrong. Give me a second. Sorry, that was a math error on my part. And sorry, this is just regular radius. There's no squared. It's going to give negative 0.1973. And we are going to answer with our magnitude for A. And then because of our negative direction, that means it's directed inward. Okay, so we're going to do the same thing for part B. So for part C, it's the same thing. We're going to want to find our new radius and figure out where that is in relation to the rest of our charges to figure out how much charge is going to be enclosed. So our R is given by R1, which is equal to 5.27 times 0.0012, and that's 0.006324. So this R is greater than R1, but it's smaller than R2. So that means it will be in between. In between the rod and the shell. So that means only encloses Q1. So our Q enclosed is equal to our Q1, which is 3.73 times 10 to the negative 12 coulombs. Now we need to find all of this all together. So we know RE is equal to 3.73 times 10 to the negative 12 coulombs, epsilon naught 2 pi, and our R is 0.006324 times our length. And let's see what we get for our answer. 7.73 12 divided by 8.854 is 12 times 2 times pi. Oops. Times 11.8 times our radius. And this gives electric field is equal to 0.898 newtons per coulomb for part C, and it's positive, so we know it's directed outwards. Okay, and last couple ones, we want to find what our electric field is at the interior and exterior surface of the shell. So the interior surface, we are just going to be enclosing, sorry. Hold on, give me a second, I'm not sure why it's negative. Okay, so at the inner surface, we know that we are only dealing with Q1 because when we have conductors, all of it just collects at the surface, right? So that means Q2 only collects at the surface over here, the outer surface of the surrounding shell, and doesn't have any charge inside. So that's why we are only using 3.73, which is our charge for Q1, for part E. And the reason it is negative, I think, is because, so we have negative charge here. We know that Q1 is positive charge. And we know that when we have electric fields, points from positive to negative. Maybe that's why. It's still outward. I am not sure. But anyways, it would be the same as our charge 1. And the same goes for our charge 2. So if we were to take it from the outside, that means we want to include the net charge from both Q1 and Q2. So that's why we would get negative 4.36 times 10 to the negative 12. So I'll just write that really quick. Okay, maybe sometime later in this video I will understand why it is negative. For now, I don't know. Sorry. Okay, so the next question is dealing with parallel plates and finding the electric field at 3 different points. We want to find it inside, on our left side, and on our right side. So we are given the surface charge of each one, which is 6.52 times 10 to the negative 22. And because they are parallel plates, this one will be positive 6.52, this one will be negative 6.52. So for part A and B, when we measure outside, okay, so again, we can explain this with electric field diagrams. So we know that from our positive, it's going to want to flow to our negative. And for our negative plate, we know that electric field lines want to flow into it, and from our positive, they would want to flow away from it. Same thing with this side. Positive flows this direction. Sorry, no, goes out of it. And that's why it points out that way too. Then we have the opposing field as well. It's a little difficult for me to explain. I'll see if I can pull up a picture really quick. So the image that I have here is a better way to explain what I'm trying to say. So for our positive plate, the arrows in green show that it's directed outwards, right? Because electric field lines flow from positive to negative. And for a negative one, they're represented by the red arrows, they're flowing into it. So basically just the opposing influence from both the plates measured on the outside will create a zero electric field. So that can answer A and B. So measure outside, we add both plates. So we know from our previous notes, for our parallel plates, it's given by 2 of our surface charge density over epsilon naught. So let's write that out. So E net is equal to this is our positive, and plus 2 for negative plate, which is equal to 0. Okay, so that is why for A and B, our electric field is 0. For B, we are going to be subtracting those 2. So that's going to give us, we can factor this out, positive 1 minus negative. It's going to be 6.52 times 10 to the negative 22 minus our negative 6.52 times 10 to the negative 22. And this is going to equal and this is equal to 7.3638 times 10 to the negative 11 newtons per coulomb. Okay, and our last question is kind of similar to our coaxial rod and shell in terms of principles of what is being enclosed and how charge behaves in conductors and insulators. For this last question, we are given a solid sphere with radius A to be 3.2 centimeters, which is 0.032 meters. with a spherical conducting shell of radius b, which is 2 times a, which is equal to 0.064 meters, and radius c, which is equal to 2.4 times a, 0.0768 meters. And we want to find what electric field is at for different distances. So we're also given charge. So the sphere at the center has a charge of 5.8 Fc, which is equal to 5.8, which is a femtocoulomb, which is times 10 to the negative 15 coulombs. Q2, which is equal to negative Q1, which is negative 5.8 times 10 to negative 15 C. Okay, so those are all the values that we are given. Now A is nice and simple to answer. So what is our electric field at 0 centimeters? So that's right at the center. So something to note about conducting bodies, we talked about this earlier. If they carry a charge at equilibrium, all of that charge distributes evenly onto the surface. So if you were to take the electric field at the center of a conducting body, it would be 0. So A is 0 newtons per coulomb. Okay, now let's talk about B. So we're going to use this equation here for electric field. So this electric field of a, So the electric field of a sphere, we already solved with our notes up here to be 1 over 4 pi epsilon 0 times q r squared. That's 1 over 4 pi epsilon 0 q r squared. But we are going to modify this equation so it also includes our outer conducting sphere. So this is going to be q over 4 pi epsilon naught r cubed at some distance r. So this capital R is of the body we're measuring. So if we change that, that would be a. And our distance r is going to be what we're going to be given for each of our question parts. So let's start with B. So B is at a distance of, so r equals a, so that's 0.032 divided by 2, which means it's going to be less than a, so that is 0.016 meters, which means we are measuring from here. So that means we are including in our equation, we'll have 1 over 4 pi epsilon 0. Our q will have 5.8 times 10 to the negative 15. So this is our q1, so it's only enclosing q1. This is times a, 0.032 cubed, and multiplied by our distance. So this is going to give us 5.8 times 10 to the negative 15 times 0.016. That's our distance of our Gaussian surface, divided by 4 times pi times 8.854 times 10 to the negative 12 times 0.032. So this is our a to the power of 3. And this gives us 0.025, 0.0245 newtons per coulomb. Now let's do part C. Part C, let's find our radius. So this is 1.5a, 5a, which is equal to 0.048. So this is larger than a, so that means that we are going to be measuring from here so we are enclosing the same amount of charge. We're only dealing with Q1. So that will give us our new distance of separation from our center, which is 0.048. We have 4 pi epsilon 0 times 0.032 cubed. So this is times 0.048 divided by 4 times pi times 8.854 times 10 to the negative 12 times 0.032 cubed. And this will give, and this gives 0.0509 newtons per coulomb. Part D. Oh, sorry. This answer is for part D. I misread the question. So it looks like we already did part D. Number's still wrong though. Okay, hold on. Okay, so let's restart with part C. Part C is measured at r equals a. So if we measured our electric field at the surface of A, so exactly the same, if we were to write that equation out, we'd have Q over 4 pi epsilon 0 times our separation, which is A. So that means this is just going to cancel. That's going to reduce down to 2. So we are going to have our enclosed charge of Q1, 5.8 times 10 to the negative 15 over 4 pi epsilon 0 a squared, which is equal to 5.8 times 10 to the negative 15 divided by 4 times pi times 0.854 to the negative 12 times our a squared. A is 0.032 squared. And that gives 0.0509 newtons per coulomb. Part D, so we already did a little bit of our part for that. We know that we are measuring outside of A, but we are less than B. So for part D, electric field is only going to be enclosing Q1 again. This is E equals and let's do the same thing where we keep our A variable in there. (1.5 A). That means we could cross that out, reduce that down. So then we have 5.8 times 10 to the negative 15 times 1.5, 4 pi epsilon 0 A squared. That's equal to Okay, I think I'm doing something wrong, but it should equal out to 0.02262. Let me find out what I am doing wrong. Just give me a quick second. Okay, in our equation, it's actually going to look something like this. I'm so sorry. So once we rearrange everything, this is going to look like Q over A squared, 1.5. A 1.5. Then this is all squared. So I have to multiply those together first. So we get 5.8 times 10 to the negative 15, 4 pi epsilon 0 times 1.5, 0.032, all squared. There we go, there is our answer. 0.0226 units per coulomb. At E, we are measuring what it is at 2.30 A. And we see that it's equal to 0. Now, why is that? So let's see where this is first of all. So for E, our radius is equal to 2.30 times A, which is equal to 0.0736 meters, which is greater than B but less than C. So R is greater than B, less than C. That means it lies in here. So our point would be in between. And similar to question A, we know that our charge disperses to the surface, so when we measure it within an object wall, that means it would be equal to 0. So that is why our electric field for E is equal to 0 newtons per coulomb. And same goes for F. And now we want to find the inner and outer shell for G and H. So, like our previous question, for our inner surface of the shell, it's only enclosing our Q1. So we would just use negative Q1 for what we're enclosing, so that makes it negative 5.8 times 10 to the negative 15. And the reason it is measured at 0 at the outside of the shell is because we know that Q1 is equal to Q2. So if we did Q1 plus Q2, they're the same charge, same magnitude, opposite charge. So that means it's just equal to 0 when we add it all up. All right, so that brings us to the end of our practice questions. These examples help outline principles of Gauss's law, principles of electric fields, principles of conductors, and how we can use electric field lines to illustrate how to solve certain problems relating to Gauss's law, electric field, and electric flux. Thanks for watching.